Okay.
Can you not put that clip of me in the beginning, please?
I won't.
Okay.
I feel like everyone should know what
For $1.
Ooh,
For $1.
honestly.
That's a high price.
Really, it's not.
It really is.
Really, it's
That's
not.
4 quarters. It's less
I
than a
only
bag
make
of
$7.25 an hour.
M&M's.
Actually, wait.
Okay. So, this is the last kind of good news, bad news day of the year.
Wait, really?
Yes, that's
Oh my gosh.
I'm seriously gonna like start sobbing. I'm so
I finished my research
research right now. I'm gonna like.
I don't have
Good news,
any.
bad news.
So, there was no homework, right?
Oh my god.
But now
But
for
wait,
really
but
bad news.
Yeah, we just waited tomorrow. Okay. But tonight, and then you have the whole weekend to work on it. So, yeah.
That means we just have all on Monday.
In theory. Yeah, Coach Broadman told me, you ought to see the lunchroom. It's all because of you.
I'm laughing. We don't eat lunch. Like,
Yeah, we don't always bring our lunch.
Okay, anyway, so back to our story. So,
Fun fact of the day.
okay, so are there any specific questions on the assignment from yesterday?
12.
Yes.
12?
Yeah, 12.
12.
I do not have 12.
What?
No, but I forgot.
Okay,
I couldn't find the concrete on the
okay. So,
brick
if
or
you look
concrete?
on this
Brick.
handy dandy sheet, okay, you've got your different thermal expansions. So
Look
it
at that.
says, like, brick or concrete, 12 times 10 to the negative 6.
I did not see that.
Yes.
I really did not see that. I was like,
Wow,
how are
so
we
you didn't do
supposed to
any
get?
of
You needed that for like half the assignment.
Oh well, I saw the. I just didn't see brick or concrete. I looked all over for concrete and I could not find it.
All
I found the
over
iron.
Satan's but alphabetical order.
Now, you'll also notice that iron and steel has the exact same thing, right? So, when you look at some of the good things that have happened for us to be here in terms of an advanced civilization, the Romans actually were the first ones to figure out how to make concrete, which is why their civilization, you know, they were viewed as like, you know, hey, we're the big deal, because of the fact that they could make concrete. They actually stumbled upon it. So the short version of how you make concrete is you take limestone, you heat it up in a kiln, it gets really, really hot, you pulverize it, and then you add water to it, it turns into a slurry, it hardens, boom, you get concrete. So if you look at how much concrete is used in this world, I mean, this entire school is a big concrete slab. They've literally, this entire school is one big concrete slab. Your basement walls, okay? The ability to use that to be even, look at these walls. Every one of, well, except this isn't, but like a lot of the walls around the doors, those are all concrete walls. If we did not have limestone, which was formed millions upon millions years ago by a whole bunch of dead little crustaceans that died and settled to the bottom of an ocean, we would not have the capacity to make concrete. And so without concrete, bad things are going to happen, or we'd have to build everything out of wood if we didn't have that availability of concrete. So having concrete's a cool deal. So when you look at how you build, if you've ever poured concrete, concrete itself is pretty strong, but they figured out if you put steel, or what's called rebar, in the concrete as it's poured, it makes the steel a lot stronger. Well, this concrete and the steel is going to thermally expand and contract. So one of the cool things that happens is that concrete and steel have the same thermal expansion rates. If they didn't, so if you look at what happened yesterday where I had the strip that was two different types of metal and I heated it up and it curved, okay? Well, that's because they had two different rates of thermal expansion. if concrete and steel had two different rates of thermal expansion, it would bust loose from itself. You could not use steel to reinforce concrete. Because, or if let's say concrete didn't have any thermal expansion at all, then that would be just as bad. Because then when the steel would heat up, it would try to expand, but if the concrete couldn't move with it, it would just destroy itself over a period of time because one would be expanding and the other one wouldn't. So we'd like to say that we had to plan that way. And again, when you look at whoever decided, hey, let's let concrete and steel have the exact same expansion rates, that was a good thing for us. Derek?
Okay, so what happens? Why do you always look at me like that when I
I don't look at you in any way. I don't even have my glasses on. You're just a blur right now.
Am I a handsome blur?
A blur.
Oh, okay.
Shut it.
So if you put something where it can expand and then heat it up, what happens to it?
What do you now? If what?
If you put something somewhere where like can't expand, like just a block of steel and it can't move,
Then it's going to bend. Which is what happens. No. He's got a legitimate question. This is why you put, as next year, or excuse me, next Wednesday, it's supposed to get really cold down to like 17 degrees.
What?
Okay?
Oh.
Yes, I'm just telling you, the high isn't even supposed to
Is
be
it
above
gonna
freezing
snow
next
at
Wednesday. So, here's the deal. If you look at this table, what has the biggest expansion coefficient? Ice does. Okay? Ice has the largest thermal expansion. This is why you put radiator fluid in your radiator. Number one, it keeps it from boiling over. It also lowers the freezing point, because if you just have straight water and that water circulates around your engine block, if that water freezes inside of that engine block, it will literally crack your engine block. So that's why you have to, they say, hey, winterize your car, check the amount of radiator fluid in it. And the level of, and you can, it's a simple gauge, it's just how many little plastic beads float in a sample. But that's how you can check at basically how low that can go without freezing. Because if that water freezes inside your block, ice expands greatly when it freezes. It's going to crack your engine block. So that's what happens if you don't give it room to expand. Okay? So like, did we talk about the SR-71 Blackbird yesterday?
Yeah.
yes.
Okay, yeah. So that's the same idea. So they had to leave room for that to expand, because if they didn't, that metal would buckle.
15.
Okay? Yes, ma'am.
On 15,
Yeah?
I know you did that example.
Yeah.
But I couldn't remember if you said, like, the larger one will bend or the smaller one.
Well, here's the deal. So you've got aluminum and copper, right? So let's say this is the aluminum on top, and let's say the copper is down below. Okay? Here's the aluminum. I'm going to heat both of these up. Which one has the larger expansion rate?
Copper. Aluminum. I'm
Aluminum
sorry.
does, right? So because these are glued together, then this aluminum is going to try to expand more, and the copper is going to prevent it from doing that, because the copper isn't going to expand as much. So since this copper isn't going to expand as much, it's going to bend down like this. Okay? Now, if they weren't glued together, if they were just side by side, and they were just sitting there and not glued together, what you would see is that aluminum would expand a little bit more than that copper does. But because they're glued together, it's going to bend down in that direction.
Okay.
Okay?
Thank you.
Does that make sense?
On the, like, on our test, will we have to, like, look at those two? Like, do we have the chart?
No, you have to have them all memorized.
Well, I'm saying, like, do we have some like that where you got, like, this chart to look at?
This is why I have a laminated version.
Oh, there is a laminated. Okay, cool. Just wanted to double check.
Allie?
Okay, I'm assuming that in number 8, when you say number 1, you mean number 7.
Yes, I did. That was
There are a
initially
lot
number
of
1, and then I inserted some stuff.
There's a lot of typos on this one. Just saying.
Oh, back off me.
There's a lot. That's why I was confused on that question, because you put
Yeah,
an extra
it's
2.
referring to number 7.
So, like, on number 12.
Number 12, that extra word.
Yeah, don't.
I made a few edits.
I was like thinking about it.
Now, on 13 and 14, I don't care if you work in square meters or cubic meters or square centimeters or cubic centimeters. If it were me, I'd just leave it in centimeters. Okay?
What's the answer roughly on that?
Hold on, where is that?
On 13, it's going to involve a 1 and a 2
Cool.
in terms of your change. Okay? On 13, your answer is going to involve a 1 and a 2.
Yeah, because I subtracted.
Your answer to 14 is going to start with a 3.
It's about the time to get a bit by price.
It's 40 centimeters squared, right? 40. Because you have to take 20 times 20. You did meters up here, and then you changed it, so this is technically in meters.
No, because I did not
Doesn't
measure
matter
that.
now. Okay.
Did you?
Anything
the
else?
area, isn't it? The length times the width, then you'd get.
What?
400.
Twice? 18?
17.
I
Okay,
don't know what.
this is what I showed you yesterday. I did this demo yesterday. Yeah, because imagine that the piece of metal was still in there where the hole was cut out. If that metal is still in there, it's going to expand from the center out. So the hole gets bigger. Nice sweater.
Did you get?
Anything else?
13, did you get 5?
Once, twice, so. Okay.
Goodness.
Raise your work Christmas better every day December.
400.
Or decommitment.
Are you gonna get the right answers?
I thought you had to.
You can watch since it just gave you an A.
All right, so here's the second to the last big topic. And that's thermal energy. So if you look at, again, what's allowed us to be here having this conversation, to have electricity, to have, a civilized world. One of the most important things we figured out is, number one, how to make water boil. And you wouldn't think, well, what's the big deal? Put it on fire and boil. So, first off, we figured out how to have an exothermic reaction, burning wood, coal, natural gas. Eventually we got really involved and we started using nuclear reactors to boil water.
They kill each other.
Hammett, just don't. Just don't. If you feel the urge to say something, don't. So, if you look at that ability to boil water and produce steam, that was one of the big breakthroughs that we made in terms of being able to generate electricity. Because the short version of you having lights and electricity to recharge your phone, your calculator, or whatever, is our ability to produce electricity. And the short version of electricity production, sort of a wind plant or solar, is that water boils, it turns into steam. We take the steam, that steam has a tremendous amount of thermal energy. The thermal energy runs into a turbine. The turbine spins a generator. It creates electricity. It goes through the wires. We can make toast. So the short version of you being able to make toast or charge your phone or do anything with electricity is that something had to spin, some turbine had to spin, generally created by electricity or created by boiling water. Now, there's a couple of things to look at. We're going to spend a lot of time talking about water. If you look at how the world is, so contemplate this. Right now, water freezes at 32 degrees Fahrenheit, 0 degrees Celsius. Okay? Imagine how life would be different if water froze at, say, 50 degrees Fahrenheit. How would things change?
We'd be living in a frozen world.
Yeah, basically Canada would be maybe even as far down as like Nebraska would basically be a glacier. Okay? Much more of this earth would be covered with ice. Now, the advantage is, we'd have a lot more snow days, okay? Because instead of water getting down to 32 degrees to have snow, we would have snow at 50 degrees.
But would it be like
We would have winter.
No, did you not just hear what he
snow?
said? Yeah.
It'd just be at 50 degrees.
So snow would be warm and still exist.
Yeah. What's arbitrary? What's hot? What's cold?
What's our temperature in Celsius?
9 in Celsius, about 35, 36.
So we could like hold snow and it wouldn't melt.
No. 50 degrees Fahrenheit.
Oh, never mind. That's what's exciting.
We probably have less snow days though, because we're like, gonna be used to it.
We have
Well,
some
but
heavy
there would just be
duty
a lot more of it.
school.
So, water boils at 100 degrees Celsius, okay?
We probably have tunnels.
If water boiled at, say, I don't know, 90 degrees Celsius, okay? Water would boil at a lower temperature.
We'd be dead.
So, no, we wouldn't be dead, but it would be, our life would be different.
If water boiled at 90 degrees.
Celsius!
Oh.
I'm so
Why'd you go from Fahrenheit?
Yeah, you're
on.
Celsius.
You are the one that did that to yourself.
I thought you just said Fahrenheit.
Yeah, you definitely.
I did say Fahrenheit when I was talking about when it was gonna freeze.
It was a valid question.
Okay.
Yeah, because obviously.
All right, okay,
Water boiling
let's
at
just,
12
we'll all
degrees
stick with
Fahrenheit
Celsius,
or
okay? Celsius or Kelvin. Okay, so if you look at the unique properties of water, okay, literally whole lectures can be, I could give a 2-day lecture just on the properties of water. So the cool thing about water is, number one, it sticks enough that it stays together as a liquid. But yet it isn't so bound together that things don't dry. So if you look at what's called the intermolecular forces that hold water molecules together, they're strong enough to hold them together. We have liquid water. Because if those intermolecular forces weren't strong enough, water would never exist as liquid. It would only exist as a vapor. We wouldn't have oceans. Life wouldn't have evolved. So it was cool with the fact that the water has this property to stay together as a liquid. But it also then is relatively easy to break that bond and change it back into a vapor. If that bond was a lot stronger, it would be hard to get things to dry. So you get out of the shower, dry off, okay, throw your clothes in the dryer, whatever. Hang them out on the line, whatever you want to do. Things are going to dry, okay? You're going to break those bonds. If those bonds were a lot stronger, it would be much more difficult to get things to dry. Your hair would stay wet longer. So we exist within a pretty cool continuum of these unique properties of water. So when you look at this chart, okay, so reference yonder chart. So what you have over here are what's called, this chart says specific heat of various substances. Some of you might have seen this in your Chem 1 class or Chem 2 class. So we're going to spend a little bit of time talking about this. Now, here's what's different about this in terms of how physicists do it versus how chemistry does this equation. Chemists deal with much smaller quantities, so their values of specific heat are joules per gram degree Celsius. With physics, because we're dealing with larger quantities, it's joules per kilogram degree Celsius. So if you look down this column, you'll notice that if you get down here to water, okay, water has a very, very, very high specific heat. It's the highest of anything on here. Okay? Liquid water has a very, very high specific heat. So what that means is that water has a tremendous capacity to hold energy. So if you get water up to 100 degrees, it's going to have a tremendous amount of thermal energy to it. So when water cools down, it releases that energy. So it used to be back in the days before they had, central heating and all of this good stuff. When people wanted to stay warm at night, they would take a kettle of water and they would put it on the stove and they would get it hot. They would take that water and they'd pour it into like a heavy plastic bag. And they would put that bag underneath the sheets of their bed. Then as the night went by, that heat would get radiated out and then it would stay underneath the blanket. So that's how people would stay warm. Or some people would they'd take a brick or something and they'd put that on the stove and get that warm. And they'd put that underneath the sheets. That was before you had readily available heating and air conditioning systems. So water has a very, very, very high specific heat, which means that it takes a lot of energy to change the temperature of water, but once you get it changed, then it tends to hold on to that heat quite strongly. So one of the things you can do to show this, that water has thermal energy, so stop that cup of water. So this is going to take a while to get this thing to work. You got to do it a couple times. Well, the system has to get heated up.
Well, toys.
Wow. Did you build this?
Do a science, man.
That's cool.
Till the system gets warmed up enough.
Is it kind of like supposed to keep
Yeah.
going on its own?
Go, 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 go on, baby. Go on, baby.
Ah! Come on. Think I
Nope.
can. Tag someone in, tag someone in.
It's going.
Oh.
Oh. Well, I guess the theory doesn't work.
Hold on.
Yes,
Physics is broken.
It's canceled.
Well, until the whole system gets warm enough.
Nope.
Oh.
Why are you getting
I like your sweater. It's nice.
Come on, Agnes.
You're gonna heat up.
I feel like it's
Detective.
TV projector thing. Stick the whole thing in her eyelid. Would it work if you just? I guess you Yeah, just stick it in the microwave.
No, metal in a microwave.
I don't know how good that was, so.
Hey. Yeah, there we go. Oh, come on. Oh, man. I'm losing faith in you, Berg.
Oh.
Hey, I still got faith.
I don't need to do it.
Has anything you told me been the truth?
I'll never watch it.
Yeah,
Hold on.
There it is.
There it was.
There she goes.
Blow on it.
There you go. Just put a fan in front of that.
Blow. There it is.
Oh.
Ah!
Why is it?
Hey, no. No. So close. This is disappointing.
Video's gonna be so boring.
I might have to heat it up.
Maybe heat it up. Stick this in the microwave. Stick the coffee in up.
One more try. If that doesn't work, I'll warm it up.
Watch this. Now. If this goes, oh.
Oh.
Ah! Oh, you said one more. You said one more. One more. Alright. Yeah, it's like, alright, after this hand, I'm done. Well, 5 more hours.
Hold on.
Are you yelling at Mr. Krabs?
I wish you got Come on, dude. This is
baloney.
Just hold on.
It's not conserving thermal energy well enough.
I like fell down.
Oh, yeah. You're used to get it.
Yeah.
I'm broken your degree.
Transfer thermal energy through our brain.
Wait, this is on.
Is this supposed to keep going?
Yeah, it is.
Sending my energy.
Oh.
Our energy. Everybody look at it and stare really hard.
So renegotiate, it's gone.
Yeah. If you'd have given me 4 seconds.
That is dangerous me. I hate
You
you.
did not.
Oh.
She's rolling.
There we go.
There we go. Okay.
Is it going to speed up?
Yeah, well, as the system gets warmer and warmer and warmer, it actually spins faster and faster and faster. So here's the cool part about this, is that if you start with the water itself, okay, it's a liquid, you put it into a microwave. How does the microwave actually make the water warmer?
By sending particles, radioactive waves. Technically, they would be microwaves.
Microwaves, okay? Microwaves are a longer wavelength than visible light, okay? So here's the cool thing. Visible light has a shorter wavelength, which means that it has a higher frequency, which means that it has a higher energy, right? So visible light, when it hits water, actually carries more energy than microwaves do. Microwaves are actually very long. But visible light won't heat up a cup of water. Microwaves do. Because microwaves basically hit a frequency what's known as the resonant frequency of water. Resonant frequency means that it makes the water molecules vibrate. So when you put stuff into a microwave, what it's doing is making the water molecules jostle back and forth. Well, it's kind of like rubbing your hands together. So when you rub your hands together, your hands get warm. Same thing is happening in a microwave. So when you put water molecules in a microwave, basically what you're doing is that the microwaves interact with them, the photons, causing them to rub back and forth. As they rub back and forth, things begin to heat up. So they actually found microwaves. A guy had, true story, a guy had a candy bar in his pocket, and he happened to be standing beside a radioactive source, and the candy bar melted. And so he's going, okay, this is a little bit weird, because they hadn't known anything about microwaves and how it interacted with particles. So if this guy hadn't happened to be standing near a radioactive source that was naturally emitting microwaves, we wouldn't have microwave ovens, so it was kind of a cool deal that happened. So I put it in the microwave. These photons that you can't see, traveling at the speed of light, interacted with water molecules. They began to vibrate. Boom, it's really, really hot. So it has a lot of thermal energy. So when I put this on here, and eventually got it to go, thank you very much. So there's a diaphragm inside there that's moving up and down. So as that diaphragm is moving up and down, it's acting like a piston. So basically it's drawing in warm air, it's using that thermal energy to drive the propeller, and then it's exhausting it back out, which is basically the same thing that happens on your car engine. Your car engines work by exploding gasoline. A large amount of thermal energy is expelled. You take that thermal energy, it drives the piston down, you draw in the next bit of gasoline and air, that compresses, boom, explodes, your car goes down the road. So this is going to work as long as this cup is warm enough to provide that thermal energy. So we're making a mechanical system move. So in some ways, Eric, this is like magic, because of the fact that I'm making this thing spin without any direct contact with the cup. Okay? It's just drawing that thermal energy. So if you didn't know what was going on, you would walk in and you'd go, ooh, that's magic. Because there's no direct physical action that's making that propeller spin. So it's like thermal magic.
Can we put a ping pong ball in there?
In what? In the vacuum chamber? No, we'll get to ping pong ball later.
So is that eventually going to slow down?
Yeah. Once it loses that thermal energy, then it'll slow down. So water, as that cools down, is radiating heat. So if you look at the thermal energy that's being emitted, when you look at that equation, Q equals mc sub T delta T. I got the mass of the water in the cup, probably about 200 grams. The specific heat of water is very large, 4,190. So what that means is that every degree temperature change there is with water, per 1 kilogram, you release or require a tremendous amount of energy to make that happen. So as this water is cooling down, it's radiating that thermal energy. The Stirling engine harnesses that energy as it goes up and down, and we're making a mechanical system move. So energy can take on a whole bunch of different ways. In this case, it's thermal energy. Now, when you look at how we perceive energy, Brooklyn, come here. Okay? So here, all you have to do, okay? Both of these blocks have been sitting out for quite a while. They're the exact same room temperature, okay? So if you look at the little indicators, right? Little indicator strips are both at the same temperature. They've been both sitting out here all day. So here's all I want you to do. I want you to put one hand on each one and tell me what you feel.
This one's colder.
Which one's colder?
The one on my right.
So that one's colder. Okay, stick your hand up. So you perceive this one as being colder. They're at the same temperature. But yet you perceive that one. You perceive that one as being colder. True?
Yeah.
Okay, same temperature, but yet it feels colder. So your body right now is about 35 degrees Celsius. This is about 22 degrees Celsius, right? So when you put your hand on each one, which direction is the thermal energy going to flow? From your hand to the block or from the block to your hand?
From my hand to the wall,
Why?
because it's taking away thermal energy from my hand.
Beautiful, okay? So both blocks are at the same temperature, right?
Right.
So what you feel as being colder is the fact that it's a function of rate. It feels colder to you because that block has the capacity to absorb energy faster than that block does. Okay? So what you feel is cool is that rate. Now, here's the cool thing, and this is where biology meets physics. If you think about what has to happen for Brooklyn to be able to experience this, okay? So when she puts her hand down, number one, she has to have nerve endings in her hands capable of even detecting this rate of flow of thermal energy, right? So she puts her hand down, the signal there goes through her arms, up into her brain, and she goes, wow, somehow or another, I'm equating this rate of thermal energy with saying this is cooler. Okay. Then it goes to her brain, and then she says, wow, I can articulate this idea. Then she forms words, sends out as what we hear when she said, oh, this is cooler, is nothing but a compression wave of air molecules that go out. It's our eardrums. Our eardrums vibrate. Yes. Sends to the auditory nerve. We hear Brooklyn say, wow, this side feels colder.
All right, time to do drugs.
What? Too much? You really didn't want to, you're just happy to say this is colder.
Yeah, that's it.
You're happy there.
Yeah.
Okay, all right. So now I'm going to go get 2 ice cubes.
Okay.
I'm going to get 2 ice cubes. I'm going to put 1 ice cube on each one. Okay? So what I want you to figure out is while I'm doing this, you figure out which ice cube is going to melt faster. So which one's going to melt faster? We're going to put ice cubes on. So here are your options. The one that felt colder could melt faster. The one that felt warmer could melt faster. Or the ambient room temperature is the same, and both ice cubes are going to melt at the same rate. Brooklyn.
I don't know.
Take that one?
Yeah.
Okay. Why?
It feels warmer.
It feels warmer. Okay.
That one faster.
All right. So put ice cubes on both of them.
Well, that was a doozy. That's not even
So
a
it's that one.
here.
It's that one. So the one that felt colder is
Melting.
That melted really
Much
fast,
faster.
though.
It's taking more thermal energy.
oh at a higher rate. Wow. Okay.
Wow, that's our class president. Time to go home.
No.
But wait, if it's taking thermal energy, why does it?
Yeah. So here's the deal. If I let this sit long enough, what's going to happen to both ice cubes?
No melt.
They're both going to melt. Okay. So and to melt ice. Think about this. To melt ice, is energy flowing into the ice or is energy flowing out of the ice?
Into the ice.
Into the ice, right? Okay. Now, one of the key concepts that you get into when you get into like upper level physics and chemistry, which I'm introduced now, is this concept known as entropy. Entropy is the measure of the disorder of the system.
Oh, I hate that.
Entropy?
Yeah.
Oh, entropy's cool.
No, it's the worst part.
No, it's cool.
It's the hardest part.
No, it's cool. Trust me. It's cool.
Just because something's cool doesn't mean it's
Like
not.
bow
No,
ties.
it's cool. It's easy. You understand? So here's the deal. What's happening to the entropy as the ice melts?
I have no idea what entropy is.
Entropy is a measure of disorder.
It's going up.
Yeah, because it's becoming more and more disordered. We're going from a structured ice cube where the molecules are locked in place into a state of disorder, which happens to my room. Okay? My room naturally goes to a higher state of disorder. If I don't work to keep the room organized, entropy happens, right? It goes to a higher state of disorder. It's a natural process. So I got to dump energy in to break the bonds that are holding this together. Now, if I set it long enough, everything's going to melt. Eventually, if I let it go long enough, the water's going to warm back up to room temperature. So this ice eventually is going to do 2 things. It's going to take thermal energy in to break the bonds. Then once it all turns into liquid, and this is going to be important, once it all turns into liquid, then it's going to start to warm up, but not until it all melts. Now, if I wanted to reverse the process, I said, okay, class, here's the lab for the day. I want you to take that water and I want you to turn it into ice. What would you do?
Stick it in the
To do what?
Take thermal energy away.
Take thermal energy away. And to take thermal energy away, what you want to do is reform the bonds. So you want to decrease the entropy of the system by taking thermal energy out. So if I dump thermal energy in, entropy increases. If I remove thermal energy, entropy decreases. Same thing with second graders, okay? Second graders are a function of thermal energy. If I dump thermal energy in the form of sugar into a second grade class, what's going to happen? What's going to happen to the amount of disorder?
Increase.
It's going to increase. Okay? They're going to start running around, right? So, but if I remove the sugar, things are going to calm back down. So the same thing is going to happen here. Okay. So that's one way that we can talk about energy in the form of liquids, solids. Does air have energy?
Yes.
Why?
Because it's not at absolute zero, so it has to have energy.
Has to have a certain amount of energy. Okay? So let's talk about that. So here I've got a syringe, very, very big one. Okay? And I've got this plunger with an opening in it. And so if I push down on it,
It pushes it back.
What the?
You damn it.
I did not touch that.
And everything falls in class.
if I push down, do I do work?
Yes.
Why?
You're applying force over distance.
I'm applying a force over distance, right? And if I let go of it, pops back up. So is the air inside of there, when it pushes the plunger back up, doing work?
Yes.
Yes, because it's exerting a force over distance. So you've got this air pressure pushing down, right? Okay. So if I push down, okay, I get this action. So what I'm going to do, I'm going to take a little piece of cotton. Put that on there. Okay. Now, in the first instance, I'm going to push down very slowly. So, push this down pretty slowly, right? And I'm doing work, right? But nothing happens.
What did you put in there?
Just a little piece of cotton. Okay? Just a little piece of cotton. So, if I push down slowly, nothing happens. I'm doing work. Now, as I push down, what's happening to the pressure inside the container?
It's increasing.
Increasing. Because the volume is getting smaller. Therefore, the pressure has to increase. Now, if I push down quickly,
Oh, I like that.
okay?
That's nice.
And yet it's
Right.
just moving in great fire.
Okay?
Smart
Piece of
done.
cotton.
Yeah, a little-
So,
Do more cotton.
no.
Hold on, look at this.
Okay? Right?
This one is bigger.
Right?
Was it
So-
just the temperature increase?
Yeah, so basically what happened, by doing that so quickly, I didn't give the thermal energy time to escape. All that thermal energy created by the work stayed within the system. Okay, ready?
Yeah, I'm
It's a
just-
fire.
Okay, you ready?
Man.
Like, that sucks though.
You ready?
Yeah.
You were so annoying.
Oh, I missed it.
Wish you could've got it. It's that idea that I have. That is not fake or what? You're just 100% fake.
Oh, that was cool. That was a good video.
That was nice.
Yeah, let me do it on Snapchat where it's not actually slow motion. That's smart.
Oh, it was on Snapchat? No, I was on my camera.
So, but that was cool to look at. Now, here's the deal.
Put that in
If I do that slowly, I do the same amount of work, but it doesn't ignite. So if you drive anything or been around a diesel engine works off of this process right here. Diesel engine works off a very high compression ratio. So diesel engines don't have spark plugs like gasoline engines do. Gasoline engines require a spark to ignite that. Diesel engines work off of a compression of that fuel gas mixture just like this. So if you compress it very quickly, it ignites. So again, this is like magic.
That was magic.
Because I'm taking normal air that you breathe, but by compressing it so quickly, I create enough thermal energy that it ignites. Right?
That just happens because the pressure increases and it does work.
And the thermal energy increases.
Is that a potato?
No. Why? Because I said okay.
Because you want to do it so
Yeah, that's it. All right.
Is that a potato or a cannonball?
Now, you can apply the same idea to what I just did with these large ball bearings. So, if I hit them with a small amount
You
of
have to do it
energy,
over here.
nothing happens.
Reed's video.
But if I hit them with a large enough okay, energy,
Wow. It doesn't seem safe.
Sounds like fireworks.
yeah, it does. Okay, so basically what I'm doing is
What happens to the aluminum in that
a
situation?
single displacement reaction.
Man, if that just doesn't smell good. No.
Is that better than lotion? Okay.
I don't know, maybe it's a different smell.
What's
'cause,
the
like,
aluminum
okay.
look like where it hit the
See, it
water?
ranks like Christmas trees are up there.
So basically it just burnt.
And then pretty gross.
But it's all at the same level.
Okay.
Why
Now-
did it take so long to make fire?
Here's what now we're gonna do similar type thing. Get ready for this now. Okay? Here, all we should do is hold this out. Okay?
Not a smart thing to do.
So what I'm gonna do is I'm gonna take these together and I'm gonna apply them on either side of the table. Okay?
Is it a head-on collision or like
Just what did I tell you to do?
never talk
Think. Okay? So here's the deal. Again, if I hit them very slowly, right? Nothing's gonna happen. I'm gonna bring these together with a certain amount of kinetic energy, right? Now, if I go faster, what does it smell like?
burnt paper.
It smells like burnt paper. Okay? So
Kind of a little, I'm smelling now, I'm getting more of like a marshmallow smell.
right? A little bit of marshmallow. Okay? So it's the exact same idea. What I was doing was taking kinetic energy
Oh, yep, marshmallow.
and I was transforming into thermal energy. This time I'm using ball bearings. But again, if I go slowly, I don't get anything because there's no
That's kind of
amount.
putting holes
But
in it.
Something popped in my face.
this, okay, good, got that. All right.
Wow.
So I basically have made fire by changing kinetic energy into.
10 out
So
of 10.
help me if you guys pass that around.
You know what?
Okay.
Pass it around.
Okay.
Put this in there.
Now.
Put this in there. What is this?
All right.
We'll talk about
Now. So let's say that I want to strike a match. So how is striking a match? And now it gets to what we've just done.
It's the same thing.
Okay, here's the deal.
Only with flammable stuff at the end.
If I move the match very slowly across there, am I doing work?
Yeah.
Yes, but it doesn't light. So it's the same idea of me pushing down that cylinder. If I push down that cylinder slowly, I'm doing work, but I'm giving time for that thermal energy to expand. If I hit the ball bearings together slowly, I don't get fire. If I go faster and have enough energy, I get fire. Same thing is here. So if I go slowly, nothing happens. But if I go quickly,
Light the paper.
no.
Why? That's some
That's the
thermal
fun
energy.
stuff.
Yeah, that's some real thermal energy.
That's why it's
You're not a physicist unless you like paper.
Just kidding. Be happy. Okay.
I mean, I want to light a flame
I want to play.
right on this.
I want you to do that again. I didn't see it.
Lighting up.
Now, lighting a match is a very novel concept. Okay. Now, yet another example how you can use air to do work.
She took the.
It's pretty hot.
Oh, do you need it?
Huh?
Do you need this tool?
No, no, no.
Okay.
Okay. So what we're gonna do is
Magic.
no, really magic.
Are you gonna shoot him?
No, watch out. So I got a ping pong ball.
Eric, can you move up a
And
little
I'm just
bit?
gonna roll down.
Thank you.
Okay? Then I'm going to cover this in. This is just like a Mylar emergency blanket. So we're covering this in.
What if there's a fire coming that?
Then I'm going to do the same thing. No. Down here. Good.
This is about untrue.
Okay, so what I'm going to do is I'm going to draw a vacuum on the container. So right now, per square meter, there is 101,300 newtons pushing down. So when we talk about air pressure and this whole idea of PV equals nRT, everybody thinks air pressure just pushes down. Air pressure pushes in all directions. If air pressure didn't push down, then you could hide underneath the tables and, oh, I'll go into a vacuum because I'll hide underneath the tables, okay? The air pressure is all around you. It's in every 3 dimensions. So what I'm going to do is I'm going to draw a vacuum on this, okay? One of the great sayings in science is that nature abhors a vacuum. So
I was just making sure it was still abiding by
the laws of physics are still pretty cool. Okay. So I'm going to draw a vacuum, and then I'm going to puncture this in.
Oh, geez.
So at that point, a bunch of air is going to come rushing in. All right? So
You're about to shoot that much.
Sure can.
now, if you're sensitive to loud noises, if this goes like it should,
Can I try and
it
bat
should
it?
be pretty loud.
It should?
Yeah. Okay.
Like the loudest tennis ball came out?
Yeah.
Okay, I'm in the worst spot. I can't see.
I want to stand behind it.
Oh yeah. Oh, it's not that in. Yeah.
I wonder what that ball feels like in there right now.
Pretty empty.
Pretty empty.
Okay. So here we go. 3, 2, 1.
Dude, did you see that? That's crazy.
That was not my first scream. I just did a little.
Ooh.
I honestly thought that.
Okay. So now I'm going to do this again, but I need your phone because what I'm going to need a couple people. So I want to try this. So what I want to do is I'm going to do this again, and I'm going to have like a couple of smoking matches down here. So that way when I puncture it, I want to film it to see if we can see that smoke being drawn in with the air.
Ooh,
Okay? All right. So find the stuff that just went flying.
I have the stuff that just went there. Because I'm a good person.
Where's the
No,
can?
you shouldn't tell me to shut up.
Where's the paint go?
I have it on your watch.
Okay.
No way.
Yeah, that's what I'm trying to.
Kyle did.
I wish like the slow motion on this phone was like.
I want you to mirror this in.
Like the slow-mo guys.
Now, if somebody has another camera and wants to record this in,
I will.
Right behind the can.
I thought I had to go right behind.
Yes.
I want a good angle. A good.
Right behind.
Oh yeah, right there.
okay.
And then hey, somebody get right there.
That's
I got your match.
king of the
Are
mind.
they gonna be louder here?
No, it'll be louder. It'll be about the same.
I sit right here. Turn the ball with that one.
So,
Don't say anything, Kyle.
huh?
Dude, this is like a mirror. This would.
No.
Just let
Hey, come here, dude.
No.
Look at this on my
You're
phone.
not going to be down. No. If you can find a way to leave your phone, that's fine. If you're willing to sacrifice your phone, you're not going to be
Just hide
behind.
behind that bucket.
Yeah.
Turn the bucket up.
Put your unprotected iPhone 7 up there.
Exactly.
Hold on.
That's where
Kyle, turn the bucket
Kyle,
on.
that's right where it flew to.
Hey, you know what you can do.
Are you good?
I'm pretty sure.
Okay, if anything happens to your phone, this is on you.
All right.
Okay,
You didn't put it in writing. Yeah, you
Okay,
gotta put it in. It's still
so-
continue.
I would not
get the
stand
matches,
there,
we'll
guy.
get those smoking, right? And then we'll see if we can see that being drawn in. Are we ready? Everybody ready?
I'm so scared.
Oh, that looks so cool. It's like upside down
Yes.
now.
Okay.
That's cool.
Oh.
You took too long, Bird.
Okay, we ready?
Not really.
I'm gonna need to.
That was a lot louder.
Okay.
Why would my phone not survive?
My shoe dropped.
Even bit.
Dude, this takes so long to melt. That's crazy.
I mean, you can see it doesn't have this.
I feel like you need
all the
an
smoke,
angle,
all the
you need-
smoke in
you need
the
more
area.
smoke. You need like an angle point.
Watch that.
Yeah.
See that 30
Okay.
seconds on there the whole time.
So,
I didn't get it.
okay.
Look at this.
What'd you get? Okay. So basically what happened is that you had about 14 pounds of air come rushing in here. Now, was work done on the ping pong ball?
Yes.
Yes, why?
Because it accelerates.
And there was a force exerted over a distance, right? So we changed the kinetic energy. So in this situation, we didn't use the thermal properties of air. We used the fact that this air was going to come rushing in and shoot it out the end. Pressure. Pressure. Okay? Got it? Good? Back we go.
Okay, we're going. I'm just.
Got it?
Why is so much cooler over here? Oh, I love it.
We
Because
took
there's
all
so
the-
much thermal energy going on over there.
Okay.
That's why.
Now,
And there's fire in there.
these equations are on the back of your big dog equation sheet, okay? There's three different Q equations. MC sub P, mass times latent heat diffusion, latent heat vaporization. I'll explain what all of these mean. So let's start with this first idea. And if there's ever an equation that kind of makes sense, this one does. So first off, Q is going to be a measure of your thermal energy. What's any form of energy measured in? Joules. Joules. So I have to get that in joules. Now, if you think about this, so let's just look at a couple of examples. I give Kendra a thimbleful of water and give her the task of raising that from 20 degrees to 30 degrees Celsius. Okay? That's your task.
Hiccups.
Now, I give Garfield a 5-gallon bucket full of water, and he has to raise it from 20 degrees to 30 degrees. Obviously, which one's going to take more energy?
Yeah.
Garfield, because he has a lot more water to heat up. So this is why this is directly proportional to mass. Now,
And then
if I take,
exhale till you can't.
in this case, I'm changing mass. Okay, more mass, same change in temperature, the value goes up. Now, if I give, whoop,
We believe in you, Bird.
now, if I give Maddie a thimbleful of water, same amount of Kendra's, but Maddie has to change hers from 20 degrees to 50 degrees Celsius. Which one's going to take more energy? Maddie's, because there's a greater change in temperature. So as mass goes up, that takes more energy. As change in temperature goes up, that takes more energy. Now,
What's CP? Specifically.
the wild card we haven't talked about yet is C sub P. And this stands for specific heat. Now, if you look at the units on specific heat, it's joules per kilogram degrees Celsius. So if you look at water, the specific heat of water is 4,190 joules per kilogram degrees Celsius. So what that means is if you have a kilogram of water, like yay much, okay, kilogram of water, and you want it, let's say you want to take from 20 degrees to 21 degrees Celsius. That means that's going to take 4,190 joules of energy to make that happen. Now, to give you some perspective, if I take this 1 kilogram mass, which is like 10 newtons, and if I lift it 1 meter, how much work do I do? I take it 1 kilogram, which is 10 newtons, roughly, and I lift it 1 meter, I do,
9.8, whatever.
let's just call it 10. Okay? I do 10 joules of work, right? So, to take 1 kilogram of water and change it 1 degree Celsius would be the equivalent energy of me doing this 419 times.
Wow.
Okay? So, when you all get out on your own, and you start to pay your own natural gas and electrical bills, I promise you, if you want to reduce your electrical bills, don't stand in the shower and take long, hot showers, because of the fact that it takes a tremendous amount of energy to heat up that water. So a large amount of your utility bills are going to go to heat up water, because it has such a large specific heat. So when you're out on your own, if you want to reduce your electrical bills, don't use as much hot water, because then that way you don't have to pay as much money to heat that water up. But the good news is once it gets heated, it retains that energy, or then you can give off so much energy. So if you look at what happened when we had the cup, okay, that cup of hot water, and we had that Stirling engine on top of it, that water was cooling down. So as that water cooled down, it was giving off this energy. That energy was being harvested basically by the engine. It made the propeller spin. Now eventually the propeller stopped, because the system has lost enough energy that we can't harness it anymore to keep that thing spinning. Eric?
Okay, so does it take the same amount of energy to make water colder by that amount?
Well, it's just that amount of energy that has to be removed. So if you're going to warm it up, you're going to dump in a certain amount of energy. If you're going to cool it down, you're going to remove the same amount of energy. Okay? Now, let's talk about these two numbers here. This is mass times what we call latent heat of fusion, and then you have latent heat of vaporization. And again, on your chart down here, you have this table, right? And you'll have this table for the test. You just have to know how to use it. The main ones we're going to use are for water. So there's a couple of things that are unique about latent heat of fusion and latent heat of vaporization that are different from the Q calculations involving change in temperature. So if you look at these units, these are just joules per kilogram, okay? You'll notice that there's no change in temperature here. Same thing here. So if you're talking about latent heat of fusion, that deals with the melting or freezing of water, alcohol, whatever it is. Latent heat of fusion deals with the boiling process. So this is how much energy, if you're going to talk about melting ice, so if you look at that chunk of ice that we use, if I know the mass of the ice, and if I come in here and I look up that latent heat of fusion for ice, which is 3.33 times 10 to the 5th joules per kilogram. So if I had given Brooklyn a kilogram of ice, you would take 3.33 times 10 to the 5th joules of energy to melt a chunk of ice. Now, if I gave Brooklyn a kilogram of water and said, hey, Brooklyn, I need you to change that into ice, she'd have to remove 3.33 times 10 to the 5th joules of energy. So, if you're going to melt it, that amount of energy is flowing in, you're increasing the entropy. If you remove that energy to make it into ice, you're decreasing the entropy because you're taking the water molecules and locking them into place. Now, if you look at water, if you want to boil water, now come over there and look at that. That's 22.6 times 10 to the 5th. So this is like an order of magnitude higher. So it takes a lot more energy to boil water than it does to melt water, like an order of 10. So this is why it takes so much energy to make water boil. So if you look at what's going to happen, a lot of times when you talk about this process, you talk about what's known as a temperature and energy graph.
Oh, yeah, I know, yeah. That is what it's.
So, one of the first things that you have to figure out is this difference between temperature and heat. They're related, but they're vastly different things. Okay? They're very much related, but they are not the same thing. So, here's the classic example. If you look at a match. So let's say that next Wednesday the high is supposed to be 31 degrees. It's going to be really, really cold. You walk into your house, and for whatever reason, no one's turned on the furnace yet. Okay, so it's really, really, really cold in the house. And you think, wow, so cold. I just watched this lesson in physics. Oh, I have a match. I will strike a match. You're not going to burn down the house. Okay, you're just going to strike the match. So, is striking that one match and having that ignite going to be enough to warm up your house?
No.
No. Will you burn your hand? If you hold your hand right on top of it, you'll burn your hand. Okay? But you're not going to warm up the house. So when you talk about temperature, okay, when you talk about temperature, I'll never expect you to know this equation. I'm just going to write it up on the board. To calculate temperature, temperature is basically a measure of kinetic energy of the particles that are inside. And this is going to be an important thing to understand. So, to calculate the kinetic energy, which is a reflection of temperature, don't write this down, I'm never going to expect you to know this. The kinetic energy of a particle is 3/2 times what we call Boltzmann constant times temperature. Okay? That's it. Oh, don't worry about this. So, what this tells me is that if I have a particle of oxygen, nitrogen, carbon dioxide, doesn't make any difference. If I want to know the kinetic energy of that particle, it's only dependent upon the temperature. This is a constant. It's known as Boltzmann's constant. Don't worry about it. It's just a constant. The 3/2 comes from a statistical analysis. The main thing being is that kinetic energy of a particle is only dependent upon the temperature in Kelvin. So as the temperature goes up, the particles have more and more kinetic energy. So it's like second graders.
Hold on.
Okay?
I am so confused why. This makes me upset. Because we have this equation, right? K equals 3/2
Boltzmann's constant
times B. Okay, it's always going to be the same number, so why don't they just take 3/2 times B and just have it be that number? So what's Boltzmann's constant?
Because it's like 1.36 times 10 to the negative 29th joules per Kelvin.
All right, then make it 2 point whatever.
No.
Why?
Because what this is going to give you, here's what's important about this. Okay? If you have a hydrogen atom, which is or a hydrogen molecule, very, very small, and you have carbon dioxide, which is the exact same, at the exact same temperature, they're going to have the exact same kinetic energy. But here's what you want to look at. Kinetic energy is 1/2 mv squared. So that carbon dioxide molecule, which is that you've got 2 carbons, okay, or 2 oxygens bound up. That's a pretty big molecule. Then you have little hydrogen over here, okay? They're both going to have the same amount of kinetic energy. So that means the hydrogen has to have a higher... No. If I have both of these gases at the exact same temperature, they're both going to have the exact same kinetic energy. Same kinetic energy. This is very massive, so it has to be moving slower. The hydrogen, to have the same kinetic energy, has to be moving much faster. Now, here's the significance of this. If you think about the mechanics of taking the temperature of a system, let's say that you have that water, that cup of water back there, and you put in a thermometer. And let's go the old school where it has like the mercury or the alcohol inside of it, right? The old school ones, not the digital ones. So basically what happens, what creates temperature, are these particles colliding with that thermometer. And we've realized, wow, we can take those collisions and have that reflective based upon the height of that reading in that thermometer. Now, as that water cools down, what happens to the level in that thermometer? It's going to go down because the particles inside of there are hitting it with less and less kinetic energy. So what we measure as temperature is a reflection of an atomic interaction of these particles colliding with that temperature probe. So when it's really, really cold at 17 degrees next Wednesday morning, you take a thermometer outside and you go, wow, it feels really, really cold. Okay? It feels really, really cold because of the fact that it's similar to what happened with Brooklyn. You're going to have a large rate of thermal loss. So if you stand outside and you go, well, it's not that cold, and you walk out with short sleeves and shorts, okay, guess what? You're going to get really, really cold really, really fast because your body has a very, very high temperature, a lot of kinetic energy, and that energy is going to flow out. So why do you wear a coat when it's cold? What are you trying to reduce?
The thermal loss.
The loss of thermal energy. You're trying to prevent that. So when it gets cold outside, that's what you're doing. You're trying to reduce that flow rate of thermal energy. Now, if Brooklyn had had a glove when she put it on the one that felt colder, guess what? It wouldn't have felt colder because she wouldn't have had the thermal loss. So as it gets colder and you all start wearing sweaters and scarves and everything else, basically all of that material is doing one thing, trying to reduce the flow of thermal energy. So you can view thermal energy as being like a fluid, and it goes from where it's hot to where it's cold. So when Brooklyn put her hand on there, shit felt cold because that energy was flowing out. Now, let's go to this graph. What? Okay. So, I give you a task. Okay?
Did you? Okay.
Sam grilled cheese. I'm going to give you a chunk of ice at -10. And I want you to warm that up to 0 degrees. Are you going to dump energy in or take energy out?
Dump energy in.
Right? Because you're going to warm it up. You want to give this stuff more kinetic energy. You want to raise the temperature. You want to increase the kinetic energy of the system. Right? So, anytime there's a change in temperature, you're going to use this. Q equals M delta T C sub P.
That's for an increase?
Any change in
Any
temperature.
change.
In this case, I'm warming it up. If I was cooling it down, I'd still use the exact same equation.
You have that.
Okay?
Damn it.
Quit throwing things.
That was a
It's a magic drop. Now, here's the deal. When you look on this chart, if this was Sam's job, and he's going to calculate this, he's got to use the specific heat of ice, which is 2100 joules per kilogram degrees Celsius. So, he'd have the mass in kilograms. His change in temperature would be in degrees Celsius, which would be 10. And then the specific heat is in joules per kilogram degrees Celsius. So the kilograms are going to cancel out. The degrees Celsius cancels out. He's left with joules. Obviously, the bigger the chunk of ice, the more energy that's going to take. Now, at this point, it's ice at 0 degrees. But I need to get it to water at 0 degrees. So Brooklyn, what direction does energy have to flow? Into the ice or out of the ice to melt the ice? Into it, because I'm going to break bonds. This is the other universal axiom. Anytime you break bonds, you dump energy in. When you form bonds, you have to take energy out. So I got to break a whole bunch of bonds. Now, when this line flattens out and I'm melting it, then I'm going to use Q equals M, then I'm going to use the latent heat of fusion. Now here's the cool thing about latent heat of fusion. If you look at the units on latent heat of fusion, those units are joules per kilogram. Okay? Multiply that by kilograms, the kilograms cancel out. The reason that there isn't a change in temperature with latent heat of fusion or latent heat of vaporization is because the temperature isn't changing. That's what temperature change isn't there. If I dump energy in here, I'm changing the kinetic energy. If I dump energy in here, I'm not changing the temperature, I'm not changing the kinetic energy, but basically what I'm doing is I'm storing potential energy because I'm making these bonds vibrate more and more and more. Then, once they all get broken, then it's like, free at last, free at last. Then, I can start changing the temperature. But you've got to break the bonds that hold it together first before you can change the temperature again. Now, this is why this is just mass times your latent heat of fusion. Temperature isn't a factor here, okay? Because you're not changing the temperature. You're just storing potential energy to break those bonds. Now, from here to here, now it's liquid water. What are you going to do? Now you're going to warm it up, right? Now you're going to have a temperature change. So in this segment, I'm going to use this value again. I'm going to use Q equals M delta T C sub P. Mass of the water. Now, what's going to be my change in temperature? I'm going from 0 up to 100. So now I'm going to have a huge change in temperature. But now I'm going to use the specific heat of liquid water because that's liquid water. This line, water is going to be boiling. Why is this line flat? Where's the energy going?
Potentially.
Yes, because now I'm going to store that to break the bonds that hold the water molecules together. Once it all gets heated, and now it's steamed, then I'm going to use a change in temperature again. So, anytime there's a phase change, you use latent heat of fusion or latent heat of vaporization. Anytime there's a temperature change, you use this equation.
And
okay?
The units for both of them are the same or
yes.
different? And it's joule per kilogram?
For LF and LB, they're both joules per kilogram. Specific heat, though, is joules per kilogram degrees Celsius. Okay, good enough. No, you don't.